we finished the last session talking about scripts, and today we're also going to just talk about Bitcoin scripts. So remember that in the last session I said whenever we have a transaction and this transaction has an output, the output of course has a value, which is like the amount of Bitcoin that is put there. And we also use the word coin to refer to the output. So I can say this is a coin or an output, and it has some value. But then it also has a bunch of conditions that need to be satisfied in order for you to be able to spend that coin. And we said that these conditions are written in a scripting language. And when we are taking the output of a previous transaction and entering it as an input to the current transaction, we have to give some parameters to the script so that these parameters actually satisfy the conditions. And if the script that was written for this output returns true, it means that it can be spent, and then we spend it in this transaction. Now, we saw one example before. So we have 3 friends who have some money and they want to be able to spend it only if a majority agrees. So this would require 2 signatures among Alice, Bob, and Carol. Now, in this course, I'm not really going to get into the details of Bitcoin scripting, because very soon we're going to switch to Ethereum, and then in Ethereum we have a much more general programming language for writing scripts and writing smart contracts. But just to talk a little bit about Bitcoin scripts, I want to tell you some of their limitations. So one important limitation in Bitcoin scripts is that they cannot have loops. So every script has to run in constant time. Has to run in O1. This means that the programming language that you have in Bitcoin for writing your scripts does not have a for or a while. It does not have functions that can call each other and create recursion. You cannot do anything that would simulate a loop. So no loops, for or while, and also no recursion. So in that sense, the programming language that we have for writing these scripts is very limited. And as part of one of the homeworks in this course, you have to go and look at this programming language and write some scripts in it. But I'm not going to cover it in the lectures because, again, it's a very limited programming language. But what can this programming language do? It can generally check a bunch of things. It can, for example, check signatures. That's one of the things that is allowed. It can compute hashes. It can also access the transaction itself. So maybe it can access the hash of the transaction. It can also access the block. So access the transaction and the block containing it. So when I say access the block, it can basically get some information about the block that contains this transaction on the blockchain. For example, you can look at the block number. So you can have a particular coin. So remember, the coin is basically the output of a transaction. So let's say this is my transaction. And let's say I have this output, which is paying, let's say, 5 Bitcoin to Alice. So when I say it's paying 5 Bitcoins to Alice, it means that the script here says that in order to spend these 5 Bitcoins, you need a signature from Alice. Okay. But I can also make it so that Alice can only spend these 5 Bitcoins after a particular time. So I can make my script more complicated, and I can say you need a signature from Alice, but additionally, the block number should be more than some number. Should be more than some constant number that I'm going to give. And again, remember that the block number is how we keep track of time. We know that there is going to be a new block roughly every 9.5 minutes. So if I want this money to be usable only, let's say, after 2 weeks, I know exactly what block number to put here so that that block is approximately going to be mine 2 weeks from now, right? So I say I need a signature from Alice, and I also need the block number to be more than some number that I'm hard coding here. And if I write a script like that, then of course only Alice can spend this output. So if there is a different transaction that is using this output as its input, let's say I have this other transaction later on. So let me call this one transaction 1, and let me call this one transaction 2. So transaction 2 uses this output as one of its inputs, right? Now, in order for transaction 2 to be valid, it's going to need a signature from Alice. So of course, only Alice can use this. So I need Alice's signature here. And basically, Alice's signature is one of the parameters that I'm going to give to this input. Remember, every input gets some parameters. So I'm going to write it inside here, but it's actually a parameter to the input. So I'm going to have Alice's signature. But in addition, let's say, I don't know, this C was 1,000. If a miner takes this transaction and puts it into a block, but the block number is less than 1,000. For example, if a miner tries to put this transaction into block 900, that's not going to work. Now, what do I mean by it's not going to work? I mean that if the miner creates such a block and then propagates it in the network, every node on the network is going to validate the block. They're going to verify that all the transactions in the block are valid. But then when they see that this input is using this output, which could only be used after block number 1,000, and the current block number is less than 1,000, they would reject the whole block. And because of that, no miner would actually put this transaction into a block before block number 1,000, right? Because if they do that, they know that their entire block gets rejected. And again, this goes back to what we have talked about before, which is like miners want to make money by block rewards and also by transaction fees. So the miners want their blocks to be added to the blockchain. And anything that endangers their income, they're not going to do it. Okay. So these are some examples of things that you can do. But here I said that we can check signatures and we can also access the transaction and like some information about the block. You cannot read the entire block, but you can access some information about it. So for example, you can access the block number. Now, the other thing that is interesting is that you can check signatures on different things. So here I was a little bit hand wavy. I just said that this output needs a signature from Alice, but a signature on what exactly? So if there is another transaction that is using this output, right? Of course, I want to make sure that Alice is agreeing to spend this money, right? Because my intuition is that this money belongs to Alice. So I want a signature from Alice to make sure that Alice actually agrees with this transaction. Now, there are two ways to look at this. This transaction, again, is going to have a bunch of inputs, let's say 3 inputs, and it's going to have a bunch of outputs, right? Now, what exactly should Alice sign? One way of looking at this, so this is variant 1, is that Alice should sign the entire transaction. Okay, so Alice signs transaction 2. So I can write a script here that says I need a signature from Alice, but I need this signature to be on the entire transaction. Okay, so I need a signature on the whole transaction to all of its inputs, all of its outputs, and metadata, and all of that. Alice should sign all of that. But here's the thing. I might want to create a transaction in which Alice gives one of the inputs, but then the other inputs can come from other people, right? So maybe Bob is contributing this one. Maybe Carol is contributing this one, and so on, right? So this one came from Alice. Now, if I say that Alice should sign over the entire transaction, this means that Alice should know the entire transaction. Alice should know exactly which output or which coin Bob is using as this input, right? But maybe that's just too much. Maybe they don't want to have that much communication. Basically, I can say that Alice should only sign on her own input and all of the outputs of the transaction, right? So if I ask for a signature like this, basically what it means is that Alice is saying, I'm contributing these 5 Bitcoins, and I agree with these outputs of the transaction. Now, these outputs might sum up to more than 5. So maybe this one is 10, this one is 12, whatever. This one is 1, this one is 0.1, right? So the transaction is going to need some other inputs because they sum up to more than 5. But Alice is going to contribute 5 Bitcoins, and she's going to sign the outputs and her own input. So she's saying that as long as these are the outputs, I'm fine with this transaction. And I don't care who else pays for the rest of the money. If someone else pays for the rest of the money, then the transaction becomes valid and it's fine. So this is our second variant. Variant 2 is that Alice signs basically the outputs. I mean, also her own input, but we can also have only the outputs, her own input and all outputs of transaction 2. Okay, this one is usually called anyone can pay, because the idea is that Alice is going to create a partial transaction. Alice is going to create only this red part, her own input and all of the outputs, and sign it. And then anyone else can come and put their own inputs here to complete the transaction. And as long as the transaction is otherwise valid, as long as like the conditions for all of the other inputs are satisfied and like the total sum of inputs is more than the sum of outputs, then the transaction can go through. So here the idea is that many different people are giving inputs to this transaction, and each one of them doesn't care about the other inputs. They only care about the outputs, right? So in my scripting language, when I say I need a signature, I can specify, do I need a signature on the entire transaction? Or do I need a signature only on my input and all the outputs of the transaction so that anyone else can pay? Okay. So these are some basic things I wanted to tell you about Bitcoin scripts, but let me show you how Bitcoin scripts can actually be used. So these are some use cases. And actually, in Bitcoin, people usually call these smart contracts, but we're going to use the word smart contracts for a different kind of smart contract. So let's call these Bitcoin smart contracts. But generally speaking, I just use the word script. Okay, so here's the first thing that comes to my mind: burning money. Imagine that you want to burn some money. So you have some Bitcoins and you just want to get rid of them. Now, when we were talking about the centralized system, the centralized cryptocurrency, we said that, well, the sum of inputs should be more than the sum of outputs. So if I want to burn, let's say, 1 Bitcoin, I can just create this transaction and I can put 1 Bitcoin in as an input, and then I can just not have any outputs, or I can have an output that is like 0, right? And that would just burn all the money, right? But now the problem is that the difference between inputs and outputs is not actually burned anymore. So if I look at the sum of inputs minus the sum of outputs in my transaction, we said that in Bitcoin, this is not burned. Instead, it's paid as a transaction fee, right? It is paid to the miner. Okay. So this is not a good way of burning money, because technically, well, you lose your money, but the money is not burned. The money is just transferred to the miner. What if I want to really burn my money? I want to make sure that this money is not usable ever again. Well, first of all, you might ask, why would anyone want to do this? Actually, there are some really nice use cases for this. For example, when you have a new cryptocurrency, sometimes you have to prove to the new cryptocurrency that you have burned some Bitcoins so that they give you new units of the new currency on the new blockchain. Okay, so there are cases where you actually need to burn Bitcoins. And also generally, people are stupid, they do stupid things all the time, so maybe I just want to burn my money. So the question is, how can I do it? Well, another way I can do it is that I put my money into a transaction and then I create an output. And remember, the simplest type of output that I could create, and let's say this is 0.99, because in order for the transaction to go through, I have to pay some transaction fee. But I'm burning the majority of my money. Now, in order for this output to be burned, I have to make sure that no one can access it. Now, one way to do this is to just use an invalid public key. So remember, the simplest way that we had here was that we said we require a signature from some public key in order to spend this. So I say, in order to spend this output, I'm going to require a signature. But this signature is going to be required from a public key that is obviously not a valid public key. So from an invalid public key. So for example, I don't know, I say I want a signature from the public key, this 00 invalid. 00, okay? This is not a valid public key. No one has the corresponding secret key. So if I require a signature from this public key, no one can provide it. So this money is effectively burnt, right? But here's the thing, because we have scripts, we can do this in a much simpler way. Remember, I can spend this money only if I can give some parameters to this script so that it returns true, so that it allows me to spend it. So I can just do something like this. I can create my transaction, and then I can just have some input going into it. Let's say I put 1 Bitcoin into this transaction, and I have some output, again, a little bit less because I have to pay some transaction fee. And then here as the script, I just write a script that always returns false. So it's a script that would never return true. It's a script that would never let you spend the money. So it's just burning the money. Okay, so this was the simplest use case of scripts. Now let me give you a better use case. So consider a scenario like this. So I want to do a deposit. And so this is my scenario. Let's say you want to join some group, or you want to join some website, but this website is afraid that you might be a spammer, so there has to be some cost for joining. Okay, so I want to join some website, or I don't know, some page on Reddit, or I want to join, let's say, a forum, but the forum wants to avoid scammers or spammers, sorry. So it wants to make sure that there is a cost to joining. Okay, so there is cost to join. Now, of course, they can just ask for a membership fee, right? They can say you have to pay us some money. But at the same time, imagine that I want this forum to be free. So no membership fees. I have a website. Anyone can come on this website and create an account. I don't want to charge them any membership fees. But then the problem is, if it's free, someone might create thousands of accounts. And then, well, they might just spam, and I don't want that to happen. So there should be some sort of a limitation on how many accounts you can create, but I also don't want you to pay me So the solution is to put a deposit. Okay, so the solution is very simple. I say you can join if you deposit some amount of money. Let's say you deposit, I'm gonna say 1 Bitcoin, but this is too much. In practice, it's going to be much less than this. So you can join if you deposit 1 Bitcoin, and you will get your money back when you exit. So you'll get your money back when, let's say, you close your account. Okay. This is great because now I know that anyone who wants to join my website has to pay a lot of money. They have to pay 1 Bitcoin. But also it's just a deposit. So they're going to get their deposit back at the end anyway. So I'm now sure that no one can be a spammer and like create thousands of accounts because they will need a ton of money. They need to deposit a ton of money, and hopefully no one has that amount of money, or people who have that amount of money don't really care about spamming me, right? But now here's where things get much harder. This is the challenge. We want to do this in a trustless manner. So no one trusts anyone else. Now, what does this mean? This means that the member who's creating an account is not willing to pay me the money and just trust that I will transfer the money back to them at the end when they close their account. Okay. On the other hand, I am not willing to trust them. I'm not willing to trust that they will actually not use the deposit. So they cannot just deposit with themselves, right? Because they might use the money. So we need a solution that makes sure all of these conditions are satisfied. Now, here's what we do. We can just create a new transaction. And in this transaction, let's call this TX. There's going to be some input. And the input is, let's say, 1 Bitcoin. And let's say that the input comes from the member. Okay. There's also going to be an output. But this output, again, it's 0.999 Bitcoins, let's say. It's a little bit less than 1 Bitcoin because you have to pay some transaction fee. Now, here's what I would say for the conditions to spend this output. I say that it requires the signature of both parties. So requires signatures from both. Okay, let me call the member Alice, and let me call the website Bob. Okay, so the forum is called Bob. So this requires a signature from both Alice and Bob. And that's it. This is the deposit. Okay. So imagine that Alice creates this transaction and publishes it on the network, and some miner picks it up and adds it to the blockchain. When this transaction is added to the blockchain, now Bob can be sure that Alice has locked some money, because this money is locked here and Alice can get it back only if she has a signature from Bob, right? But at the same time, Alice can be sure that Bob cannot steal her money, right? Because in order to spend this money, I need a signature from Alice. So Bob cannot just unilaterally spend this money. So this is much better than just transferring the money to Bob. But we still have a problem here. And the problem is that Bob can basically take the money hostage. Bob can say, I don't sign. And if he doesn't sign, then Alice basically has all of her money stuck in this contract. And it's pretty much like this case. It's like the case where the money was burned. As long as Bob doesn't sign, the money is going to get stuck and you cannot spend it. Okay, so Bob can kind of extort Alice. Bob can tell Alice, hey, here's the thing. I'm going to sign only if you pay half of this money to me. So only if you create a transaction where it pays half of the money to me, I would sign it, right? So that's not great. But remember, our scripts can do more than this. Our scripts can also access the transaction and some information about the block, and especially they can access the block number. So I can change this script. I can write a better script. I can say that it requires signatures from both Alice and Bob, or if some time has passed, if the block number is greater than some number, let's say whatever, 2000, the block numbers are much larger than this in the real world, but anyway, if the block number is 2000, then it only requires a signature from Alice. Okay, that's it. So at any time, if both Alice and Bob sign, this coin can be used. But if Bob refuses to sign, then the script has this second part, which can only be used after block 2000 and only requires a signature from Alice. So in the worst case, Alice's money will be stuck here until block 2000, but after that, she can get her money back. Okay. Now, again, as usual, Alice creates this transaction, announces it on the network, waits for a miner to pick it up and add it to the blockchain and so on. And Bob also sees this. So when Bob sees this transaction, Bob knows that Alice has put down this deposit at least until block 2000. And so Bob knows that Alice is not a spammer. So Alice is somehow depositing some money every time she wants to create an account. Of course, she can create several accounts, but then she would need to put down several deposits. Okay. So this was another very simple use case of Bitcoin scripts. Now, let me show you another one. So this is called an escrow. And to consider this one, you have to consider what online websites like Amazon do. So if you have an online marketplace, the way it usually works is that you have a buyer and a seller. So a buyer, let's say Alice, wants to buy something from a seller, wants to buy something from Bob. Now, this thing is, let's say, some real world item that has to be delivered, for example, by post. But Alice wants to pay using cryptocurrency. Alice wants to pay using Bitcoin. Okay. Now, in the normal scenario, we have internet commerce. So Alice just wants to use her credit card to pay and so on. So we're going to have also a third party, usually websites like Amazon and so on, who's going to take the money from Alice, and then they're going to wait for Bob to fulfill the item. And when the item is fulfilled, they're going to pay the money to Bob, right? So I have a buyer who wants to buy something. Alice wants to buy something from Bob. And then there is an escrow agent. Let's say Carol, who checks whether the transaction was done correctly. So who checks whether Bob has fulfilled the item. Now, again, in the real world, the way it works is that Alice pays Carol. So we're trusting Carol. And Carol is going to keep the money. And when everything is over, Carol is going to pay Bob. But of course, if Bob doesn't fulfill the item, then Carol would not pay Bob. But now, as you can imagine, the challenge that we have here is that we don't want to trust Carol. We do not trust each other. Generally, we want to always have trustless protocols. So we always want to make sure that no one has to trust anyone else. Now, I'm going to give you a solution here, but unfortunately, the solution is not great. And this is actually escrows are some of the things that we're going to talk about for many sessions. So I'm going to give you a solution. And then afterwards, I'm going to give you some attacks showing why this solution is not perfect. So here's the solution. Alice creates a transaction. This is my transaction. And this transaction has a bunch of inputs. I don't care where Alice got the inputs. Anyway, these are previous coins that belong to Alice. And then it's going to have an output. And let's say this output pays the price of the item. So let's say, for example, 1 Bitcoin. But instead of saying that Bob can just spend this coin, instead of paying Bob directly, or instead of saying that Carol can spend it, I just say that it requires signatures from both Alice and Bob. Now, if I just do this, if I don't involve Carol at all, this is already a nice contract. It's kind of enforceable in the sense that if Alice and Bob do not agree, this money is basically burnt. So the only case where this money can be spent is if Alice and Bob agree on the transaction that spends this money, which is equivalent to saying they agree that the item was fulfilled, or they agree that the item was not fulfilled. So if Bob doesn't send the item to Alice, Alice would never agree to sign a transaction that pays the money to Bob. And similarly, if Bob has sent the item, he would never agree to sign a transaction that doesn't pay him the money. So if one side is dishonest here and the other side is willing to punish them, then the money gets burnt and the money gets stuck, basically. But now, again, the problem is that one side can extort the other side. So imagine that I am Bob, and suppose that I have not sent the item to Alice. But this transaction is already published on the blockchain, so this money is locked. So I'm going to create a new transaction. So this is Bob's attack transaction. And in this transaction, I'm going to say I have this coin as my input, right? And I'm going to say I pay half of it to myself, and I pay the other half to Alice, right? So I create this attack transaction and I sign it and I send it to Alice. Now, remember, I have not fulfilled the item. So Alice is not happy about this. But just look at it from the point of view of Alice. She has 1 Bitcoin here, which is stuck. So she either signs this transaction and publishes it, in which case she would get half of her money back, or she refuses to sign this transaction and then all of her money is stuck. So if Alice is rational, if Alice only cares about her own money and how much money she's making, she's going to sign this, right? So this is called an extortion attack. In this case, if I had published this original transaction, Bob could do an attack like this, and basically Bob could get part of the money. Now, it doesn't have to be 50-50. Bob could also send 90% to herself, let's say 10% to Alice, or any other proportion, right? So this is not good. This one is basically not secure. And of course, as you saw here, we're not using Carol at all. We're just using Alice and Bob. But here's the thing. This is actually something known as bit halo. And it's secure if you're sure that every side is willing to punish the other side, even if it means they lose money themselves. So in this case, if Alice was willing to punish Bob, if Alice was willing to say, I don't sign this transaction, Even though not signing this transaction would lose me money, I'm not going to sign it anyway, just to punish Bob, just to make sure Bob doesn't get the money. Then this attack would not work. Okay, so it's not secure if Alice and Bob are rational. And again, remember, when we say someone is rational, what we mean in this course is that they only care about their own payoff, and they want to make sure that they make the maximum amount of money. So it's not secure if Alice and Bob are rational, but it is secure if Alice and Bob are vindictive, if they're willing to punish the other side. And of course, the other thing I could do here is to require this first transaction to also have some input from Bob. So it has some input from Alice. I could also require some input from Bob, so that Bob is also putting down a deposit, so that when the money is locked, Bob is also losing something, right? So we could do these kinds of things. But again, our basic assumption in this course is that everyone is rational. So we're not considering the cases where someone is willing to punish the other side, even if they lose money themselves. But now, let's involve Carol. Let's create a different solution where I also have Carol in there. So I create a transaction. And so this is my second attempt. I'm going to say there are some inputs, and then there is an output. Again, let's say this output is 1 Bitcoin. Now, here's the thing. If Alice and Bob agree, of course, we want them to be able to spend this money. So when I'm writing the conditions for spending this money, one of the conditions can just be signatures from both Alice and Bob, just like before. So if I have signatures, if I have consent of both Alice and Bob, I can definitely spend this money. But what happens if there is no such consent? What happens if Alice and Bob cannot agree? Well, I can basically say Alice can go to Carol, and then Carol can check who's right, right? So I can say, if you have a signature from Alice and Bob, that's fine. But it's also fine if you have a signature from Alice and Carol. So, or signatures from Alice and Carol. And similarly for Bob. Let's say Alice is cheating. Alice doesn't want to sign even though she has received the item. So Bob goes to Carol, proves to Carol that the item was fulfilled. And then we say, if there is a signature from both Bob and Carol, that's also valid. So basically what I'm saying here is very similar to the very first example of script that we saw, which is that we have 3 people, and if 2 of them sign, you can spend this coin. Okay. Would this work? Now, this would work if you trust Carol. If you're sure that Carol is 100% honest and she will never cheat and so on, this would work. But again, remember, we're assuming that everyone here is rational. So we are assuming that Carol just cares about her own payoff. Now, what is the attack that I can do? Again, suppose I'm Bob, but by the way, all these attacks, I'm telling them from the point of view of Bob, but Alice can also do similar attacks. This is very symmetric. So let's say I'm Bob, and I have not delivered the item to Alice. And let's say that Alice is now not willing to sign. But I want to convince Carol to sign so that I can get this 1 Bitcoin. Okay. So I can create another transaction which uses this 1 Bitcoin as its input. So this coin is used as the input of this transaction. This is the transaction created by Bob. And I can say that I want to pay the 1 Bitcoin minus some small transaction fee to myself. Okay, so this goes to Bob. And again, remember, when I just say it goes to Bob, I mean that the script here says that it can be spent whenever there is a signature from Bob. Now, this input, this coin, requires not only a signature from Bob, but also a signature from Carol, assuming that Alice will not sign, right? But of course, Carol will not sign this because Carol can check and Carol can know that Bob has not sent the item to Alice. So we're going to bribe Carol. We're going to say, here, I'm going to pay whatever, let's say 0.8 Bitcoins to Bob, but I'm also going to pay almost 0.2 to Carol. Okay. Now, if I do this, then Carol would be convinced, right? Because Carol wants to get this money. And as Bob, I have created this transaction. Let's say I have also signed this transaction, and I've sent this half-signed transaction that only has my signature to Carol. So Carol looks at the blockchain, sees that this original transaction is already on the blockchain. So she sees that if she just signs this transaction and publishes it, she will get 0.19 Bitcoins. So if Carol is rational, she would help me in this attack. And she would sign it and publish it. And basically, Bob has again succeeded in not giving the item to Alice, but getting part of the money. And this was done by bribing Carol. Again, you can change these numbers. You can play with how much of the money is paid to Bob and how much of it is paid to Carol. So this one is also unsecure if Carol is rational. Okay. But it is secure if Carol is honest. So if you have a third-party Carol that you can actually trust, then you can have an escrow like this, and it would work out, right? So Carol can check, and we're sure that Carol doesn't do anything dishonest, and everything goes through. But if this escrow agent, Carol, is also rational, then this is unsecure because you can bribe Carol. Okay. Now, this is actually not a solvable problem. You cannot really get around this, but I'm going to also show you a third attempt. So this is something that actually some of my students suggested last year in this course, but unfortunately, this also doesn't work. And the idea was that we want to create a transaction like this, but we want to make sure that no one can bribe Carol, right? So the problem here was that Bob could just bribe Carol, and if Carol was rational, she would just accept this. So I'm going to create a similar transaction as before. Okay. I'm going to put this transaction here. But I'm going to make my script more complicated. So I'm going to say this 1 Bitcoin can be used if you have signatures from both Alice and Bob, or signatures from both Alice and Carol, or signatures from both Bob and Carol. But remember, my script can also access the rest of the transaction, right? So this was one of the things that my script could do. So in my script, I can also say that whatever transaction is using this coin should have only one output, and that output should be only Bob or only Alice, okay? So I take the entirety of the conditions that I had before, and at the end of it, I say, and the transaction using this coin must have exactly one output, and that output should be either to Alice or Bob. Okay. Again, I'm not going to talk about how you can actually write this script in the Bitcoin scripting language. Just imagine that you have written such a script. Now, the idea is that if I write such a script, then Bob cannot create a transaction like this, right? Because a transaction like this would basically make it impossible because it will not satisfy the requirements here. So Bob can only create a transaction that pays all of the money to himself. He cannot create a transaction that pays the money to Carol. He cannot bribe Carol like that. Okay. But here's what I can do. And again, this is a really nice attack. So again, imagine that I'm Bob. I have not delivered the item. I want to bribe Carol to sign a transaction. So I'm going to create a transaction now. And I'm going to use this output as the input to my transaction. Okay. So I'm going to use this output as an input. This is the transaction that Bob is creating for his attack. And now the problem is that I can only have one output, and this output can only go to myself. So I have, let's say, 0.99 Bitcoins, and this is only going to Bob. I cannot add a different output that pays some money to Carol. So if I just create this transaction, I cannot convince Carol that she's being bribed. I cannot convince that she's getting any money. So there is no reason for Carol to sign this transaction. But here's what I can do. I can create a next transaction. So this is the second transaction of Bob. Let's call it TX prime Bob. And I can use this output, the output of the previous transaction, as the input of this new transaction. And then here I can say 0.8 to Bob and 0.18, let's say, to Carol. Right? Now, as Bob, I create these two transactions and I sign both of them and I send them to Carol. Now, Carol looks at these two transactions. She sees that if only she signs the first transaction, then the first transaction would become valid, right? Because the first transaction will have signatures from Bob and Carol, and the output is only to Bob, so it will satisfy the requirements here. So Carol can make the first transaction valid. Carol can sign and make this transaction valid. But as soon as she does this, then this next transaction will also be valid, which means that she can just sign the first transaction, make it valid, and then publish both transactions. And miners will pick up both of the transactions, and as soon as both transactions are added to the blockchain, Carol is paid. Okay? So again, the attack is just a little bit more complicated. Bob is going to create both of these transactions. He's going to sign both of them, and then he's going to send the signed versions of both of these transactions to Carol. Then Carol sees that if she signs the first transaction becomes valid. And the second transaction is only valid if the first one is valid, because it has an input that was the output of the first one. So anyway, if Carol signs the first transaction, both of them become valid, and then Carol can just publish both of these transactions on the network, and she gets paid. So in any case, even if we write something like this, Bob can still bribe Carol. So in summary, our escrow works in two cases. It works if we have an honest escrow agent who is not rational, doesn't care if she makes money, doesn't accept bribes, then this kind of escrow would be acceptable. The other case where the escrow would work is that I'm not going to use an escrow agent. I'm just going to have Alice and Bob, but I'm assuming that Alice and Bob are not rational. So this means that if one side cheats, the other side is willing to punish them, even if they themselves lose some money. We have a question in the chat. How can the second transaction be propagated if it's not valid? Well, it cannot be propagated, but that's the whole point. So Bob creates both of these transactions and signs both of them, right? So at this point, both transactions are invalid because the first transaction also requires a signature from Carol, and the second transaction depends on the first transaction, but the first transaction was invalid, right? But he sends these two invalid transactions to Carol. He doesn't publish them on the network. And then Carol signs the first transaction. As soon as Carol signs the first transaction is now valid. And because the first transaction is valid and the second transaction is using this output from the first transaction, and it's also signed by Bob, so the second transaction is also valid because this output here only required the signature from Bob. Now that both transactions are valid, Carol publishes both of them together. And then everyone in the network will propagate these transactions, and at some point, a miner will take these transactions and add them to the blockchain. So in the end, Carol gets paid. Okay, so this is it for this session. I'll see you next week.